Ωραία. Ωραία. Επομένως μπορούμε να ξεκινήσουμε. Βασίλη, οπότε έχεις το λόγο.
Ωραία. Ευχαριστώ πολύ, Δημήτρη. Σας ευχαριστώ πάρα πολύ για την πρόσκληση. So we will change gears a little bit and I'll talk in English, but if you want me to talk in Greek, I can also do that. So I'm going to talk about some recent work that I've been doing, in fact, over a couple of years now with people at Queen Mary University in London, Kostis Papageorgakis in particular, in Queen Mary, and also postdocs and PhD students in Queen Mary. So this is about, the title is about bootstrability with improved truncation methods. So I'll try to go slowly. I will assume that not everybody is an expert on the conformal bootstrap program, so I'll try to go slowly. So this talk is about alternative strategies in the numerical conformal bootstrap program. The main methods that is been, the established method that is being used in the conformal bootstrap program, whose main idea I will describe during my talk, is the so-called linear functional method. So one of the questions that motivates the study is, do we need to explore beyond this established method? Are there any motivations to do that? And this in itself is a problem in conformal field theory. So part of this talk is about solving a problem or addressing in a different way a problem in conformal field theory. The second part has to do with the following question: do we need novel numerical optimization techniques to complement the analytical progress? As you will see, many of the questions, many of the mathematical problems we have to solve here are formulated in terms of some optimization problem. And the question is whether we can use some of the recent progress in data science and computer science to accelerate the things we learn in conformal field theory and quantum field theory in general. So a partial question here is machine learning or artificial intelligence a useful tool? And I will try to touch upon that with specific examples during my talk. So since I want to go off a little bit the mainstream way of doing things in conformal field theory and conformal bootstrap program, I want to start from the end and show you. So during the talk, I will discuss the general setup, the motivation, and then I will demonstrate everything in a particular example in the context of planar n equals 4 per Yang-Mills theory. And I want to start from the end. I want to show you the kinds of results we're getting numerically and how they compare with the standard methods. So the context we're going to discuss, the example we're going to discuss the so-called recent bootstrability story. It's a combination of the words bootstrap and integrability, which was analyzed in 2021 and 22 by Gromov and his group in King's College. And it's basically about studying correlation functions on the wall volume line of a half BPS Wilson line in planar n equals 4 per Yang-Mills theory. So one of the things that are, so in planar n equals 4 per Yang-Mills theory, you can use integrability to determine the spectrum of non-BPS operators, unprotected operators. But one of the things that has been very difficult to do is to compute correlation functions, in particular three-point function coefficients. So the idea that they had was why not use the information from integrability to get the spectrum and then implement this in the conformal bootstrap program to read off three-point function coefficients. And they managed to do quite well, to get results, very nice results for 3 OP squared coefficients, which is for the first time a non-perturbative computation of non-protected CFT data at the non-perturbative level in n equals 4 per Yang-Mills theory. They use the standard method that I will quickly explain. One of the technical difficulties of this method is that it runs, when it runs, it requires a lot of digits. It requires a lot of precision. So they were running with 1,000-digit precision at each step, What we did is a different method that I will explain, which I will call improved truncation, which runs at, it's much cheaper, and it runs at machine precision. So it only requires 16-digit precision. And as you can see, the results are very much comparable. In particular, C1 squared here agrees up to the 7th, 8th digit. And this is a calculation at hoofed coupling, which is at order 150. Okay, so let me start the first part of the presentation, which has to do, as I said, with a problem in conformal field theory. So as you know, conformal field theories are particularly a simple subclass of general quantum field theories. I'm going to be discussing the standard case of conformal field theory in any dimension in flat spacetime. And what makes them particularly well behaved is that basically we can learn everything about them at the level of local data if we know what operators we have, in the sense of, we know their scaling dimensions, and also if we know their 3-point functions. So one of the powerful elements of conformal field theory is that they have a convergent operator product expansion. So you take two conformal, two conformal primaries, two operators. You bring them together in space-time, and then you can replace them by, in general, an infinite sum over other operators. And there are certain coefficients that appear there. So part of this product has to do with the space-time dependence of the operators. It's sort of like a Taylor expansion, but you know these functions here, these f hat functions, explicitly because of conformal symmetry. So they don't depend on the theory, basically. What depends on the theory are the fusion coefficients, these 3-point function coefficients. But you see, once you have a structure like this, then basically you can use it inside any n-point function to reduce it down to basically 2-point functions or 3-point functions. So knowing the scaling dimensions and the 3-point function coefficients allows you in principle to determine any n-point function. So this data, the scaling dimensions and the OPE coefficients, is what I will call the CFT data. This is what we're after to compute. So let me apply this quickly in a 4-point function. We take, for simplicity, these are 4 scalar identical operators. You can fuse them like you can fuse 1 and 2, and then 3 and 4, and you get a particular expansion simply by substituting, by doing the OPE twice, once for 1, 2, and once for 3, 4. This will be 4. And then you get an expansion that involves the OPE square coefficient. So you get an OPE square, OPE coefficient from here, OPE coefficient from here, they are squared. And then you sum over all the operators that are flowing in the intermediate channel. And then everything that depends on the space-time points is explicitly known. You solve it once and you're done. It depends on this block here. This is called the conformal block. It depends on the scaling dimensions of the operators that run in the middle, and this we don't know. So you have a very complicated, typically in even dimensions, these functions here are hypergeometric functions, or combinations of hypergeometric functions. So you have a highly nonlinear function of the scaling dimensions that appears linearly. The dependence on the OP square coefficients appears linearly. Now, the point is that this can also be expanded in a different way, where you fuse 1 and 4, and then 2 and 3, and then you get a seemingly different expansion. And this relation here is called the crossing symmetry equation. It's a consistency condition. It's basically the associativity of the OP algebra. And the idea of the whole conformal bootstrap program is to solve these equations here without even using a Lagrangian. One of the things that the standard method uses is the positivity. If you have a unitary theory, you have the squares of real numbers. So these coefficients here are explicitly positive by unitarity. And I should also say here that because of conformal invariance, the space-time dependence is highly constrained. Basically, you get the dependence only on 2 numbers, which are these ratios, dimensionless ratios the space-time points. So I'm going to be using U or V or Z and Z bar, which are equivalent in this way here. So this is the general setup. The general setup is that you write down these equations, and in general, you get algebraic equations of this form, and you want to solve them for the C's and the deltas. What makes this interesting and complicated at the same time is that this has a functional dependence on the cross ratios, or what I call Z and Z bar here. And there are infinite number of unknowns, C's and deltas. And you also have an infinite number of 4-point functions that you can consider. So every time you write down a 4-point function, you get a sum rule, if you want, and you have to solve all of them together. So obviously, the complication here is that you have to work in an infinite dimensional space. Okay, so what's the standard method? What are people using since 2008? So this goes back, this idea, as you know, idea goes back to the 70s, work by people like Polyakov, where they imagined that maybe we can solve a theory non-perturbatively by solving these equations. It turned out that they made some progress in 2 dimensions with rational conformal field theories, but then the project was dropped, basically because it was very complicated. But then in 2008, Ratazzi, Ryzhkov, Tony, and Fitzy managed to make a very smart observation. Basically, they set up this kind of logic here that allows you to extract non-trivial information without actually solving these equations. So what's the idea? The idea is the following. First of all, you take this equation, which is linear in the OP coefficients. You apply a linear functional on it. This could be a derivative or a sum of derivatives or anything evaluated at some point. And then once alpha acts on these conformal blocks, it basically gives you a number. So it could also be an integral or the evaluation on a particular point in the cross-ratio space. It gives you a number. And then every time you apply one of these alphas, you get a sum rule. You get basically a sum of an expression that involves the unknown C's and the unknown deltas, and it's some infinite sum that you have to satisfy. So their idea was to make some general assumption from the beginning, say that all the scaling dimensions that appear here in the sum, are above the unitarity bound, and let's single out one of them, like say the lowest one, and assume that there is a gap in scaling dimension, and then try to search for alphas for which alpha acting on all the f's that appear here is explicitly positive. And say we normalize it so that if the identity appears, alpha on the identity contribution is 1. Then if you can manage to find such an alpha, you see this equation cannot be satisfied, basically because you have a sum over positive numbers, strictly positive, some of them, and others can be positive or equal to 0. But then obviously this is going to be a strictly positive quantity and you cannot satisfy this equation. That tells you that if you can find this alpha, the assumption is eliminated. And this way you can eliminate assumptions. So in sort of like a more machine learning kind of language, this is essentially a classification algorithm. You make an assumption and then the algorithm tells you that it tells you no, this assumption is inconsistent, or it tells you that maybe you can satisfy this assumption. By the way, I should emphasize here that finding these linear functionals here is converted into a convex optimization problem at the end of the day. Now, what is nice about this method? The nice thing is that this gives you rigorous results. Once you make an assumption and you eliminate it, you know that it's eliminated. Also, you see, you start changing delta mean here, and by changing delta mean, you can find allowed and disallowed regions for your CFT data, like in this famous plot here, where they try to get bounds like this for 2 scaling dimensions in the 3D Ising model, and they notice that there is a region which is not allowed and a region which is allowed, and then there is the boundary between them. Another nice thing about the method is that you can use it to make generic statements for conformal field theories, and sometimes you also notice specific features in this on the boundary of these allowed regions. Sometimes you get this cusp, and then they noticed, for example, here in this example, that the 3D Ising model is the theory that lives there. Or if you make more assumptions, then the problem is sufficiently constraining, and you get, instead of something like this, you get an island, and maybe it's a small island, or you can go to a point, and then you can really focus on a theory. The other useful thing here is that there is a powerful programming method to implement this algorithm, which is called semi-definite programming, which is a semi-definite programming method, which was set up and is now the mainstream by Simon Staff in 2015. And as I said, this is convex optimization. Obviously, convex optimization is much, much simpler than non-convex optimization. Okay, these are the benefits. What are the negatives? The first negatives will be obvious. Typically, when we make assumptions, these assumptions are blind because we haven't solved the theory. Maybe we're interested in some theory, we know very few things about it from other methods, but mostly we make blind assumptions. And then obviously it's easy, like in a case like this, I can start changing delta epsilon, delta sigma, and try to find what is allowed, what is disallowed. But imagine trying to do this with many parameters in a high dimensional space. Obviously, it's going to be impossible. So it's difficult to scan high dimensional parameter spaces, and for that reason, it's very hard to explore. And also, it's very hard to do what I call solve my theory. So if you're interested, like me, for example, I'm interested in solving the QCD in the conformal window, then it's very hard to do with this method, basically because I don't have a priori all the assumptions that I need to focus on that particular theory. Another thing that this method is using crucially is the positivity of all these OP squared coefficients. And this is not in general available. So for example, if you try to do the similar thing, not for 4-point functions, but for higher point functions, the so-called higher point bootstrap, then you get products of OP coefficients that are not squares, and therefore you cannot use explicit positivity. Or if you do the conformal bootstrap in the presence of boundaries, again, you have OP coefficients multiplied by 1-point functions, and then again, it's not manifestly positive. Or if you have non-unitary theories that are sometimes interesting, you cannot apply the same method. So there are many, many contexts where you can simply not apply this method. Another disadvantage is that the semi-definite programming methods are powerful, as I said, but they are expensive. I already gave you an example where at each step we had to use 1,000-digit precision, and this is generic. Now you might say, okay, if it works, why do you bother? Maybe you need to, stress your computer a little bit more, but it's not like this. Basically, the more interesting case is when you try to solve several of these crossing equations together. This is where the bootstrap becomes more constraining, but then this high precision demand becomes a very expensive method, and basically the technical improvements over the last few years is to try to understand how to put this, on to do parallel computing with this in computing clusters. So it requires a lot of resources. Now, given this, it will be desirable to supplement this method, which obviously has some benefits, with other methods, and this is what I want to discuss. So before giving you a summary of how we implement things, let me try to give a list here of what I would like to have. Like if I wanted to construct a new method, what features would I like it to have? First of all, I would like it to be as algorithmic as possible. I do not want to assume positivity because I want to have access to many generic cases. And I want to put emphasis on guided exploration towards solving my CFT. So instead of asking generic questions about conformal field theories, I want to be able to use it, like, for example, lattice QFT. I want to use it as a method that solves the theory that I'm interested in. So for example, if I want to solve conformal QCD, I want to be able to use it as a tool to solve conformal QCD, which means that I should be able to generate some of these assumptions that are blind in the standard method. This will entail incorporating all available information. So that includes the definition of the theory in some parametric regime. As you can see, this method doesn't use any Lagrangian or anything standard that were used in a QFT course. So that makes it inherently non-perturbative, but on the other hand, you want to be able somehow to define your theory, right? So you want to input the information at that time, solving that particular theory, and having a Lagrangian achieves that. So you want to include the definition of the theory in some parametric regime, any analytical information that you can get, etc. Secondly, another thing you want to have is you want to have cheap and efficient high-dimensional searches. You want it to be efficient with multiple correlators and any other available sum rules. For example, constraints from integrated correlators that are becoming more and more functional. And as much as possible to have controlled systematic errors and have a setup where you can integrate with other standard methods like the linear functional method. Okay, so the moment I mentioned the word, the moment I mentioned the goal to have a method that doesn't use unitarity, there are not a lot of options. And basically, immediately you think that, okay, I have to solve these equations. Obviously, I cannot take them because they are infinite dimensional. I cannot put them on computer like this. So the obvious thing is to truncate them. So this goes under the category of truncation methods, which offer an alternative. They have been studied a little bit in the past, but they are not the mainstream. And the reason they are not the mainstream is because they are notoriously messy and they have lots of systematic errors that you cannot control. So let me examine the issues that you have, how you proceed in this way and what issues you will encounter. Okay, so I'm taking the same crossing equation that I had before. I'm slightly rewriting it in the following way. So in this crossing equation, you have some unknown data, some unknown contributions with unknown C's and unknown scaling dimensions delta n. But imagine that you know some contributions, basically because it's something simple like the identity contribution, or you're solving the crossing symmetry equation in super conformal field theory. And there you can use information from protected data from supersymmetry, basically. Then you take that information, you plug it in, and their total contribution I summarize here in a non-explicitly known function that I will call R for the rest or remaining or whatever. The first step is to discretize the ZZ dependence, which is standard, also in the linear functional method. You can do that by evaluating this equation at specific points in a collocation lattice, or you can compute Z and Z bar derivatives, which is the standard, the usual practice, around a point. A convenient point is the crossing symmetric point. There is analytic results that you can derive that tell you that these conformal block expansions converge exponentially around this point, and that's good because it means that a few terms or a finite number of terms is enough to get good accuracy. So, okay, so this is my equation. Now I evaluate on a lattice or take derivatives, and that gives me the possibility to take out of the infinite set of equations that I have to select some of them. And I write the equations in a vector form. It's still an exact system of equations, so I haven't made any assumption, any approximation so far. I just picked a subset of the full available equations. The second step is to identify a subset of the most significant operators in this infinite sum. So you say, oh, I'm going to select a specific finite set of these contributions, and I'll try to track them explicitly. I don't care so much about the rest. I will incorporate in some tail contribution. Now, the choice of what you include here, like you have operators at this spin, and then you say, I will include the 10 operators of that spin. You go to the next spin, you say, I will include 15 operators of that spin, is something we call the spin partition. Basically, it tells you how many operators per spin you should include in this explicit sum. So then this equation, which is still exact, takes the following form. I've just split the contributions. It has a contribution with a finite number of terms which you want to track explicitly, and then the rest you don't want to track explicitly, but you care about their sum contribution. I will call it T, vector T for the tail. Okay, so far it's generic. I haven't made any approximations. The next step, which is the common step 3, which is usually goes under the title of truncation methods, is to look at this equation and say, how am I going to solve it? right? And obviously the thing that you don't know or you don't have any degrees of freedom to track dynamically is this tail contribution. So you say, I'll set it to 0. You assume that you have included enough operators here so that this thing has converged, and the main contribution comes from this operator. So this was first, I think, analyzed in some detail by Gliozzi in 2013. His logic was pretty simple. You basically you set this by hand to 0. You treat the rest of the contributions, you set them explicitly to 0. So although you basically truncated, you dropped some piece, obviously you're not going to satisfy these equations exactly now, but you pretend that the truncated equations are equations. You write more constraints than unknowns, and then you get an exact over-constrained system that you try to solve. So you look at subdeterminants if you treat it as a linear system with respect to C, and you try to make progress. Obviously, there are lots of ad hoc assumptions here, and the method is not very well motivated. And also, technically, when you do these truncations, typically people solved it with Mathematica, for example, and if you go to order 10 operators, it becomes impossible. So you are forced to very drastic truncations in this way. In 2017, when Yang Li reformulated this a little bit in a more natural way, he said, okay, these are not exact equations. So what I want to do is basically take this contribution that I want to evaluate, which is, and when it's not 0, it's basically the error from, how much I deviate from exactly satisfying this approximate fake equations. So you have this error vector, and you want to minimize that. So you make a cost function, and you minimize that. And that already, for those of you that have heard a little bit about machine learning, this already takes us into the realm of machine learning. So now, in doing that, you have a function which is explicitly written in terms of the unknowns C and the scaling dimensions that appear inside this conformal block. So you have a highly non-trivial, non-convex optimization problem that you have to solve now. Again, in this paper, he didn't apply this to anything non-trivial. But in 2021, we thought that we started thinking about this as a large-scale optimization problem. So we thought, okay, it will become better if you can solve this problem with many, many operators. And we were thinking that the larger the subset of operators you include, the better. Now, as you will see, this is not as straightforward as this, but these papers basically began the debate of how to solve this as a high-dimensional optimization problem. Now, I want to so far I'm trying to, if you want, introduce that approach. Now I want to try to sort of criticize this approach, tell you what are the problems, okay? Why is this not good enough? First of all, it's not algorithmic. So you can ask, how do you select the operators that you include these important operators? You don't know, you haven't solved the theory. So how do you know how many to include? So in previous approaches, these operators were selected essentially ad hoc, or they were trying to rediscover some known theory, and then you have some, you cheat a little bit and you put the operators that you know that are important. The second question is, what is the effect of the infinite number of operators in the drop tail contribution? Maybe you can justify dropping the tail, say, at small coupling if you have some parameter, some coupling, but then as you change the coupling, the tail contribution becomes large and you have to include more operators. I mean, how do you know? The third question is, if you try to include, some gauge theory, for example, and start including operators, and you start enumerating operators, as you go up in scaling dimension, the number of operators very quickly grows. And you have an exponential number of operators, and many of the operators also are very close together in scaling dimensions that are near degeneracy. So you have a spectrum that is essentially chaotic, many near degeneracies. It has a lot of, many chaotic features. It's very complex. So how are you going to track all this complexity and the large number of operators as you try to increase the number, the scaling dimension of your cutoff? The fourth point is that unlike what we were expecting by adding more operators, this is not a straightforward optimization problem. And this is indeed very, very similar to what people are encountering when they're trying to do similar optimizations for parameters in neural networks in machine learning. Again, there you have the parameters of the neural network, and you have some cost function that you try to minimize as you train the neural network. And this is, that you may have millions of parameters there, so you have to do optimization million-dimensional space. And that landscape of that loss function, or the cost function, is a high-dimensional multinodal landscape with very complicated microstructure. It's basically glassy. And there are many configurations with comparable cost value. Now, in the context of machine learning, this is a good feature, having lots of configurations of comparable low cost value, because basically you don't care a lot if you did very well with your optimization. You land in one of them. There are many possibilities, and many of them are equally good for your purposes. But here we have a slightly different problem where we don't care about generic configurations. We care about the specific configuration that solves our physical theory. And we also want to be precise. We want to be accurate. So we sort of have a higher standard. And also, if you look at this landscape in generic situations, you have multiple bases of minima. So you have this glassy behavior, and then there may be like a basin here, a basin there, and they have different costs. But you may not be interested in the global minimum. Both of them may be equally good approximations of different physical theories. So you want to explore, if you're interested in the spirit of solve my CFT, if you're interested in a particular one, you care about one of these minima and not the global minimum. And that means that the fastest optimizer, like for example, stochastic gradient descent or whatever you use in machine learning, may not be the right optimization tool here. And another final point is that related to the complexities of 3 and 4, adding more operators does not necessarily improve the accuracy of the result, because as you add more operators, the algorithms are dynamically changing the scaling dimensions. So one of the options that they have to make the problem dynamically simpler is to take many scaling dimensions and basically put them close together. And then effectively all these closely packed operators are behaving like one single contribution. So it's like putting less operators in your spin partition. Okay, good. So what do I want to do now? So now I want to change this viewpoint of the standard truncation methods and introduce a new viewpoint, which I will argue moves closer to the original picture of the method of Ratazzi and company from 2008. I will still do truncations in a particular way, but I will try to incorporate or approximate the contribution of the tail, so an infinite number of operators. And in this way, I will move closer to the original discussion. Okay, so what's the setup? So instead of focusing on a particular CFT, I want to focus now on families of conformal field theories. So I will assume that there's some parameter. I will call it collectively lambda here. It could be one parameter or many parameters. It can be discrete or continuous. It could be a coupling, for example. So you can continuously change it. Think about some Lagrangian, you have some coupling, you continuously changing. I want it to be CFT, so in that case, if it's a continuous coupling, it has to be an exactly marginal coupling, and we have cases like this in supersymmetric theories. Or it could be a discrete parameter. It doesn't have to be a coupling. It could be the rank of a gauge group. Like, for example, in conformal QCD, in the conformal window, it could be the number of colors and the number of flavors. Now, I want to be in a setup, and this is part of the assumptions, where I can solve, there is some particular value of these parameters, I will call it lambda star, where I can solve the theory explicitly. So typically, this is going to be a weak coupling regime where the theory becomes weakly coupled, and then I can use standard methods, Lagrangian methods, to solve the theory. Or it could be a regime where the theory is strongly coupled, but it has, for example, a weakly curved gravitational dual. So supergravity duals are cases of lambda star. That already improves one, where the problem was, remember the question is, the question in problem one was, how do you set up the problem? How do you choose the operators you have to include in your spin partition? Once I go to a particular regime where I know the theory, I know roughly how the spectrum behaves, at least in that particular corner, and that gives me motivation on how many operators to include. Obviously, as I change lambda away from lambda star, things can rearrange, but at least I have some regime where I can track my operators, or I have some idea about the structure of the spectrum. The second step I want to take is not to drop the tail, but approximate it, and that will improve problem two. So the first thing you can do is do what we call a static approximation. So you go at the known solution point, lambda star, and there you assume that you know explicitly you have solved the theory. So you know basically all the in the infinite operators, the CFT data that appear in the tail, so you can compute the tail. Now, the nice thing is that you don't have to sum an infinite number of CFT data. Even in free field theory, that could be hard to obtain sometimes, because you have to do very complicated weak contractions. But you can use the crossing symmetry equation, which is obeyed exactly here. You have a finite number of terms, the tail, evaluated at lambda star, and that explicitly known function. And then you can solve for T star. So you can basically compute a finite number of CFT data, sum them like this here, and solve for T star. And this way, you know indirectly the contribution to the tail exactly at lambda star. So then the approximation here, the static approximation, is to say, okay, these are operators at high scaling dimensions. They are supposed to have a small contribution, and you know, as operators have large spins, for example, they are going to behave as free fields essentially. So, you know, they are not going to depend a lot on lambda. So why not make a more nuanced approximation here, where I say, I do not set T to 0, but I say that T doesn't vary a lot away from lambda star, at least in some regime, some neighborhood of lambda star. So you plug this T star inside the exact equation. The exact equation becomes like this. And then you see, in terms of this error function, in this error vector, it takes this form. Basically, E minus E star is almost equal to 0 with this approximation. And then you try to minimize the new cost function, where you're not trying to minimize the cost of E alone, but the deviation of E from E star. So in this way, you're already starting with a point where you can actually have zero cost exactly, and then you move away from that. Now, how do we incorporate, how do we treat the complexity of the spectrum or nearly degenerate operators? Now, assume that you have a band of nearly spaced scaling dimensions, and they have some exact contribution. As I said before, if they are close enough, you can approximate them by a smaller number of operators. You don't care about the CFT data of these operators. You only care about their total contribution. And including a small number of them is enough to capture, in general, the contribution of maybe 1,000 operators, a large number of nearly spaced operators. So in this way, when we have situations like this, we don't want to track, you know, the infinitesimal or very small differences between operators that are closely packed. It's like the gas of atoms in the room. We make an effective description, and so we want to include a smaller number of operators that are effectively capturing the contribution of the exact operators inside our crossing equations. And now you can do the same thing also for the higher dimensional operators to improve that static approximation of the tail. If you go to your subset of operators, the operators that you have chosen to put explicitly in your spin partition, you can take the higher dimensional contributions and treat them as effective operators. Your tail is not exactly the correct tail. So when you optimize the high scaling dimension operators are going to be affected by the errors you are introducing. They're going to try to adjust to fix the error. So again, for these high dimensional operators, you don't want to read off specific CFT data. You have them there as extra degrees of freedom to try to correct the mistake that you did by including a particular approximation of the tail. And this is what we call the dynamical soft tail. Now, an interesting thing here, when you get down to the practicalities, is that different optimization algorithms in this highly non-trivial, non-convex optimization problem seem to behave differently, and they seem to treat the soft tail contribution differently, which is interesting. Okay, so the other point was point 4 about the complexity of the landscape and you know, the fact that it has multiple basins of minima that you want to track locally. So you need efficiency in local guided searches without precise knowledge of the region. And as I said before, that makes the optimization hard because you cannot take, you know, most of the standard optimization algorithms out of the box and apply them there. If they try to find the global minimum, that's not what you want. So you want to do some local guided search. And for that purpose, Markov chain Monte Carlo methods, where you basically go stochastically around, you throw in some algorithm or some agent and starts going stochastically around in some particular region, explores the region. That seems to be a better strategy, or because it allows you to explore locally some particular region and you don't have to tell it, you know, search within this specific box. And this is precisely where AI and ML, in what I will show in a moment, comes in for us. Okay, so that concludes the CFT problem. So to summarize, the computational problem that we have to solve now is we include lots of, you know, we set up the spin partition, we have these crossing equations, we set up this cost function, and we have to minimize this complicated loss function. This is a non-convex optimization problem for the CFT data. It includes the actual, what I will call the actual CFT data that we're trying to read off, and also lots of effective CFT data that we don't care about their specific values. We only care about their averaged summed contribution to the crossing equations. And this you can do, now we can do it with thousands of unknowns. Okay, how do we do it? We have on GitHub a particular framework that we have set up. This framework is integrating basically a library of many stochastic and deterministic algorithms for optimization. It's called Python. It's all in Python. It's called Python Parallel Global Multi-Objective Optimizer. It was built by these two people who were trying to solve planetary motions in the European Space Agency. So obviously, you know, if you get the satellite orbit wrong, then you have a big problem. So they want a lot of, you know, they want powerful optimization algorithms to solve their problems. And they have, you know, basically anything you can think about in very nice setups where you can do parallel computing, et cetera, et cetera. And this is integrated within our problem of solving conformal field theories. Another algorithm that you will find there is the so-called soft actor critic algorithm, which has been developed for task controls in robotics. And this is a genuine AI algorithm that we used as a new stochastic optimization algorithm. So let me say a couple of words about this because I think it's particularly interesting. So this SAC algorithm of soft actor critic that was developed in it's an algorithm that goes under the category of reinforcement learning in AI, and it was developed in 2018 basically for robotics by these people at Berkeley. In this case, you know, in usual stochastic processes, you know, you are in particulars, you know, you basically do something like a random walk. But here we have a more nuanced problem where we do this well, it's not random walk, we do this stochastic motion. So we land in the landscape of CFT data and we start choosing randomly CFT data points. But we treat this as a Markov decision process. So basically, although in standard stochastic optimization, you have some fixed strategy in which, or some fixed distribution, probability distribution that tells you how to pick the next motion, the next point, your next action. Here, you have a more complicated problem, just like in robots, where you're in some particular situation, and then you want to pick an optimal strategy for the next step. And as you go along and you learn about your environment, you optimize your strategy. You also change your strategy. So a typical reinforcement learning algorithm proceeds in this way. You have an agent which takes an action, communicates with the environment. The action for us is choose CFT data. The environment gives you information. In particular, in our case, it gives you the, how well you did, how big is your error. So it gives you the value of this cost function. We call it reward by inverting it. So you want a large reward, means small cost function. And then as you go along, you also collect experience. So you have a memory buffer that remembers what was, your situation before, what actions you took, and that is used to update your policy. So where do neural networks come in? The neural networks come in basically inside this black box here, where they're used as function approximators to approximate basically the value of your state or the probability distribution of your policy. And this goes around and around, and as you go inside the room, in particular here inside the environment of the CFT data, you learn the landscape and you optimize. Before I go to the particular application, which is the last step, I'm going to apply this now. It's not obvious that everything I described is going to work nicely, so we have to test it. And the test case I'm going to report here is an application in the Wilson line CFT in 4D equals 4 per young mills. It's a 1D CFT application. So technically, what we did there is we did 2 sets of run in the Queen Mary high-performance cluster that they have there. We did runs with one of the algorithms that we found works. It's a deterministic algorithm that we found works pretty well. We also tested other ones in PyGMO. It's an interior point algorithm. It's highly optimized, so we could run in 15 minutes. We were getting the result, and we're running about 10 to the 8 agents. With SAC, which is an algorithm, a custom implementation that we did on our own in Python, it's less optimized, and it was much harder to do parallel runs in terms of availability that we had in the scheduling, etc. So we only did 200 parallel agents, and it was much slower. So its run basically took about 12 hours. Okay, so one of the things I want to discuss is how this performs compared to this. And you see, technically, they are worlds apart, right? One runs with 10 to the 8 agents, the other runs with only 200 agents. The optimization problem we tried to solve has 124 data, so a few hundreds of safety data. We could include more, but we didn't because it didn't seem that there was any benefit in that. And when I write down this vector of crossing equations, when I discretize it, I take derivatives of basically hypergeometric functions. And typically one gets in standard conformal bootstrap approaches, one has about 100 derivatives of hypergeometric functions that one computes. Here we included up to 260 derivatives or even 700 derivatives of hypergeometric functions evaluated at a specific point. And by the way, this is the first case where I saw Mathematica breaking down, but Python moving along on the number of derivatives unobstructed. Machine precision is very low. It's so we used the precision in digits was machine precision, 16 digits, so pretty cheap. So, and now I'm ready to, in the last few slides, to tell you what results we obtained. Are there any questions up to this point? Okay, so let me continue. So I'm going to apply this logic in the case of an infinite straight half BPS Wilson line in 4D equals 4 per young mills theory. So it's like a standard Wilson line in gauge theory. You have the gauge field here oriented in the time direction. But in order to make it supersymmetric, you also have to include one of the scalars, adjoint scalars in n equals 4 per young mills theory. I pick one of them randomly and I call it phi parallel. So for the n equals 4 per young mills theory has 6 scalars in the adjoint representation. And I pick one of them and the rest 5 I will call 5 perpendicular. So what do I want to compute here? What are the correlation functions that I want to consider? Basically, I want to take that Wilson line and consider small deformations or localized deformations of that Wilson line. And that can be expressed and compute correlation functions between these local deformations. And this can be rephrased as an endpoint correlator for local operator insertions on the wall volume of the Wilson line, suitably, with gauge indices suitably contracted here so that I have something gauge invariant. And the nice thing is that this is because, you put a defect there, you break, the full superconformal invariance of 4D n equals 4 per Young-Mills, but not all of it. What remains is the superconformal invariance of a 1D CFT. So now you can basically do what I said with a 1D CFT. I want the 4-point function to bootstrap to write the crossing equation. So what I'm going to do is I'm going to take one of the transverse scalars and take the 4-point function of that. And this is, I'm going to consider that theory in the planar limit. So the n equals 4 per Young-Mills theory, as you know, has a gauge coupling and the rank of a gauge group. Let's say we take SUN gauge theory. We're going to take the planar limit, n goes to infinity. We're going to take G Young-Mills going to 0 with this product kept fixed, the so-called Hooft coupling kept fixed. So we're in the planar limit. In the planar limit, I can still vary this lambda from weak coupling, small lambda, to strong coupling, large lambda. And I will also use this parameter G here, which is basically square root of lambda. Since I'm in one-dimensional CFT, I don't have two cross ratios, these functions U and V that I mentioned before, which are combinations, dimensionless combinations of the space-time points where I insert the operators. So I only have one, and this one I called he. Also, since I have superconformal invariance here on the defect, it's a half BPS defect, the operators can be organized in superconformal multiplets. There are some protected ones where the scaling dimensions are fixed. They don't depend on lambda. You change the Hooft coupling from weak values, from small values to large values. The scaling dimensions do not change. And you also have long multiplets, which are not protected, and their CFT data depend non-trivially on lambda. So a big problem is to find those CFT data as functions of lambda. So for example, you can use integrability. It was a big story for a decade where people used integrability methods in n equals 4 per Young-Mills theory to find the scaling dimensions of this long unprotected data. Okay, since I'm taking, by the way, phi1 perp, which is I'm inserting in the correlation function here, is one of the operators that is in this protected, the lowest, the smallest, the simplest protected multiplet, B1. So basically we care about the operator product expansion of B1 with B1, which has the identity. It has basically B2, which is basically phi1 perp squared, roughly speaking. It's the product, it's appropriately symmetrized in indices, etc. And then you have contributions, an infinite number of contributions of long multiplets. Now you work, you massage a little bit how supersymmetry packages things, and at the end of the day, you get a crossing equation of this form that depends on chi. It's one of these general equations that I was mentioning in the beginning. These are the C-squareds and the unknown scaling dimensions for all these delta n's unprotected appear in suitable superconformal blocks here that are explicitly known. Okay, so now let me tell you, let's apply two different methods. One is the standard method of the standard bootstrap linear functional method that everybody uses in the bootstrap community. Then I'm going to apply my improved truncation methods. So the first approach was done in 2021 by the King's group. They used integrability to fix the planar delta n's, and they used bootstrap to determine basically 3-point functions, the thing that is very hard to do with integrability methods. So the CNs that I'm computing here, basically 3-point functions of B1 or phi1 perp, phi1 perp, and then one of the long operators in these unprotected multiplets. So what they did is they fixed 10 long delta n's from the quantum spectral curve from integrability, and they tried to determine, find allowed and disallowed regions for the corresponding C1, C2, C3, basically the first three 3-point functions. So this is what they get. So you see they determined C1 squared pretty well, in the sense that, you know, the upper and lower bounds of the allowed region are very close, very close together, and effectively fix C1 squared, and I will give specific values in a moment. But for C2 squared and C3 squared, they didn't do as well, especially for small 't Hooft coupling. I mean, the allowed region is huge. Basically, you're not getting any meaningful information. Now let's do another, let's try now truncation methods. So they also tried that in their original paper. So you truncate to 10 operators with fixed scaling dimensions. And, you know, this is, and you set the tail to 0. So basically you have a sum of 10 contributions. You know the scaling dimensions in the conformal block. So the only thing you don't know are the linear coefficients in front of them. So minimizing the root mean square of that is basically a least squares error optimization, or a linear regression problem. This is very simple. You run it, and you're not getting very nice results. Certainly not, you know, as this one. So let's apply our method. What did we do in our method? We included many more operators with scaling dimensions that were varied. So we fixed 10 scaling dimensions from the quantum spectral curves. The remaining ones, 50 more, were not fixed, and they were varied. So it was a nonlinear optimization problem. And all the Cs we're trying to find. And these are the results. As you can see, they are much better now. We did it with two algorithms, this interior point algorithm and the AI one, the soft actor critic. For C1 squared, by the way, here you see, let's see, for IPOpt, you have this orange square, and then this circle with a dot in the middle is the corresponding result of the soft actor critic. The size of the squares or the circle does not represent error. It's just there for you to see. The errors are much smaller, the statistical errors in particular. So you can see that you know, we're dead on the C1 squared curve that they also got. Now the interesting thing is, if you see now the results that we get for the C2 squared and C3 squared, which was much harder to track in their method, again we see that the two methods are, first of all, within the allowed regions, but the two methods are not tracking, are not focusing on the same configuration. So here are some explicit results to see the errors, just to see the order of the errors, basically, and to see that all these three algorithms are basically honing on the same thing. It's also interesting that the SAC that is running only with 200 agents is comparing quite well with the interior point algorithm that is running 10 to the 8 agents, and it's highly optimized. And it's also very interesting that these two algorithms are sampling different regions of the allowed solutions of the crossing symmetry equations. So there's a lesson here. The lesson is that having multiple algorithms to do this optimization problem is a benefit, because you can use them to explore, basically if they give you different information, you can use all of them to get complementary information. Okay, and towards the end now, there were these people from King's, they were not very satisfied with basically these allowed regions here. So they said, okay, how can we make this a more constraining problem? And there are some extra sum rules that you can derive, you can compute analytically using supersymmetric localization methods. So there's a whole story behind this. At the end of the day, you get two extra sum rules for the CFT data, you implement them into your algorithm, and this is what they obtained, incorporating two more sum rules. You can see that C2 and C3 now are much more constrained. So we do the same thing with our algorithm, and as you can see, we're getting, extremely good results. Definitely, in the neighborhood of what they were obtaining. It becomes less accurate at higher values of G for C2 and C3, but we have also noticed that by increasing the number of agents, we can increase the accuracy and basically fall within their allowed regions. What is the benefit of this exercise? The benefit of this exercise is that for the first time, there is another method, competitive method, to do highly precise computations in the numerical conformal bootstrap that doesn't use positivity. And it's relatively much cheaper. They were using computations with 1,000 digits. We're using computations with just, basically it's not even 16 because we have to pre-generate the values of the conformal blocks, etc. So we're effectively using only 10 digits. And as you can see here, for example, we have accuracy at the level of the 7th digit, which is very impressive. And also, if you look more closely, you can see that for low values of G, we even have a smaller, our error is statistical, their error is rigorous, but our error is, in some cases, consistently at low values of G, even more constrained than what they give. So this is very promising. It's the first example where you can actually do things in a different way that doesn't rely on so much on blind assumptions or a lot of computational cost. This is, again, low computational cost is very important because if you want to do multiple correlators, they have an issue with that. We wouldn't have an issue with that. Another thing we checked is that the soft tail approximation works well everywhere from weak to strong coupling. So all these extra 50 operators that we're including there that we're not trying to track, basically they work well. They are modifying their average. Their sound contribution seems to be tracking the precise value of the tail contribution, and therefore, when we optimize, we're solving the right problem. We also make new predictions for higher states that they didn't make beyond the C1, C2, C3, C4, C5, etc. And we checked against their unpublished results, and we are always within their allowed regions. We have spotted particular things that we can change or implement that can improve our results. So we didn't try to post or to publish these results for the higher states because we can see how we can improve them even further. Okay, and then as I said, multiple correlator bootstrap is cheap and technically possible. So this is essentially my last two slides. The take-home messages is that we changed the emphasis of the conformal bootstrap program. We put emphasis on solving specific theories. In order to do that, we need to bring everything together. We need to bring together analytics. We need to bring them together. When available, we will also bring together the so-called navigator methods or other linear functional methods. It's important to combine different optimization methods. These methods that I described are flexible, cheap, and can be efficient and accurate. And more importantly, I think if you look more closely in what I described, basically we're advocating a departure from the usual truncation philosophy. We don't want to just truncate and do a rough approximation of the crossing equations. What we're trying to do by putting more and more operators and also approximating the tail, we're trying to understand the full structure of the 4-point function as a function of the cross ratios. AI power, a nice technical thing here that I think is not a standard thing as far as my experience goes in optimization, is that AI powered optimization here seems to have interesting features. The SAC agents, if you look at them individually, they're not performing great. They don't have very high rewards or very small cost. They are slow. But when you compute their average, this is in many examples, not just this one, many examples, it's impressively accurate. And this is happening with very low number of operators. So This motivates better reinforcement learning implementations in optimization, but also you can try to imagine more sophisticated things like collaborative AI, so-called multi-agent reinforcement learning, which is popular in robotics because, you know, when you have a collective of robots, you want them to communicate and learn together. So the question is whether similar implementation here will be able to learn much more efficiently the landscape of configurations. There are many possibilities for future work in different directions, not just in this particular way of doing things, and machine learning seems to be emerging as a new useful tool and source of new ideas also in our field where it has not been developed so much so far. And I can stop here. Thank you.
Ευχαριστούμε πολύ, Βασίλη. Μισό λεπτό να σταματήσω και την καταγραφή για να... Ωραία.